I am still on the quest to try and figure out whether or not a fixed graph is Hamiltonian or not. And so far, I've got a lot of ways to tell that something isn't Hamiltonian. We said at the end of class on Friday that if the disconnecting set S had more components, G minus S had more components than the disconnecting set S had vertices, then my graph was not Hamiltonian. Smallest possible disconnecting set is a cut vertex. If I have a cut vertex, I'm going to end up with two components or more. My graph won't be Hamiltonian. Well, there's a right away gimme. If I have a cut vertex, I'm not Hamiltonian. What's another condition on a graph that is equivalent to containing a cut vertex? Again, bridge. Because if I've got a bridge, both ends of my bridge, unless it's a bridge to an end vertex, at least one end of my bridge is a cut vertex. But that in and of itself makes sense. I know I can't be Hamiltonian if I have a bridge that goes to an end vertex, because then I hit the end vertex and I can't leave. And thus I can't complete a circuit without recrossing the bridge. Matter of fact, every circuit must contain the bridge twice. So it turns out that the whole reason I am finding more and more easy ways to determine if a graph is not Hamiltonian is because determining if a graph is Hamiltonian is really effing hard. And Jonah, the question you asked me, is there a nice, easy way? The answer is no. So one of the more complicated problems in all of graph theory is finding at least a sufficient condition. What's the minimum requirement I can get that will give me a Hamiltonian cycle? Because there's no universal qualifier. But I can start finding some pieces if I look carefully. But even though looking carefully turns out not to be trivial. Orr's theorem says that if G is a graph with order of G equals n strictly bigger than or equal to 3, if the sum of the degrees is bigger than or equal for all pairs of non-adjacent vertices, then G is Hamiltonian. By the way, speaking of named theorems, I had a problem in the homework. I just get back to you. A large number of you made reference to the expansion lemma. Do you know what word does not appear at all in the PDF of this book? Nowhere to be found? The word expansion. So I don't know what website you got the expansion lemma off of, but it wasn't out of the book. Come on, people. I understand looking up answers, but try to be careful about it. I have a name with this one, so if you use this name, I'm going to know what theorem you're talking about. But I said expansion lemma. I went, what's the expansion lemma? And so I started looking for it. It ain't in there. Meanwhile, what is the problem with Orr's theorem? I've got to check every pair of non-adjacent vertices. That's big O of n squared. For small graphs, I can do that by hand. Here's a graph with 200 vertices. I'm doomed. That is not going to be an efficient algorithm, is it? Okay. This is a named theorem. I should prove it. I'm going to walk through the proof here at light speed. I'm not going to write out the whole proof. But this is a proof by contradiction. If it's proof by contradiction, where does it start?
Suppose the opposite of the if.
So suppose, well, the opposite of the if. Not the opposite of the if, but the if and the opposite of the conclusion. So suppose I've got a non-Hamiltonian graph where this thing still applies. So I know this degree condition is true for every pair of non-adjacent vertices. What's more, I know there's no Hamiltonian cycle. So I'm going to start adding edges to my graph. Eventually, what happens? Well, it might be that if I add an edge, I still have not gotten a Hamiltonian cycle, right? I added an extra edge, still not Hamiltonian. I add more edges, it's still not Hamiltonian. Eventually, what happens? I've added all the edges I can possibly add. What graph do I have? And if it's complete, it must be Hamiltonian. Why?
Every vertex is like all the ones in the graph.
Yeah, complete graph, everything's adjacent to everything else, right? Which means at the very worst, I have a cycle all the way around all of the vertices, right? because everything's connected. So I could go from 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9. No matter what order they're physically in, everything's connected to everything else. That means somewhere along the way, in adding edges, I went from not Hamiltonian to Hamiltonian. Yes? That means there's some edge where once I add that edge, it's Hamiltonian. And the one right before that is not. What does that tell you about that one edge? G was not Hamiltonian. I started throwing on edges. Eventually I get to Kn if I add all the edges. But that means somewhere along the way we hit this graph H. H itself is not Hamiltonian, and the next edge I added is Hamiltonian.
H would have a cut vertex, didn't you get it?
Oh, wait a second. I said if it's got a cut vertex, then it's not Hamiltonian, not the other way around. That's my problem. I don't have a characterization for Hamiltonian. I only have things that I know, well, if it's this, then it's not Hamiltonian. Not a bad idea, but let's think about what happens with the is rather than the isn't. Here, I add this one edge, xy. All of a sudden, it's Hamiltonian. What do you know about the edge, xy? Not necessarily, because if I have a bridge, then I can't be Hamiltonian.
Part of the separating set.
Vertices are part of separating sets, not edges at this point. That set S was a separating set of vertices. Everything on this side is Hamiltonian, right? So let's think over here. Kn has a Hamiltonian cycle. I take away one edge, I have a Hamiltonian cycle. I still have a Hamiltonian cycle. I get to here, I have a Hamiltonian cycle. I take away xy, I don't have a Hamiltonian cycle. What do you know about the edge xy? It has to be part of the Hamiltonian cycle, because without it, we don't have one. So wait a minute. H is not Hamiltonian. right? So if I took away that edge from the cycle, I'd have a path from X to Y, wouldn't I? And that path would be Hamiltonian. It would touch everything else, except it wouldn't finish the cycle. I don't know what this path looks like. But I know it goes through all the vertices. Okay, wait a second. Now let's look at that degree condition. Let's look at that degree condition. Somewhere in the middle of this list is a vertex xi, right? Suppose x1 xi is an edge in H. I claim for every vertex before that, it cannot be adjacent to the last vertex. Why? Because I could go from x1 to xi and then back to something to xn. Wait a minute, that's a Hamiltonian. But then if I start here at xi, I can go back to x1, then go to whatever is up here and go to xn, and I all of a sudden have a cycle. It starts and ends at xi. Okay, wait a second. What does that tell you about the degree going on here between xn and x1? Okay, wait a second. For every vertex in x2 through xn that is adjacent to x1, there's another vertex in x1 up to xn minus 1 that's not adjacent to xn. That's our xi up in that sentence up there. For each one that is adjacent to the first one, there must be a corresponding one that's not adjacent to the last one. It might be different for each of them. And I don't know what the degree of x1 is, right? But that means that the degree of xn is less than or equal to n minus 1 minus the degree of x1. We said x1 is x and xn is y. Those are not adjacent in H, right? What do we know about non-adjacent vertices? We know that the sum of their degrees is bigger than or equal to n. Not according to that. There's my contradiction. There's a lovely picture, fumble, of this statement in the textbook showing you why those two things can't both be true at the same time, about the way in which we create a cycle when they are the same, true at the same time. So I think that visual might help a little, but I've very roughly done this proof. But once again, this is not a trivial thing to compute. It is a major pain in the ass to go through and check every pair of non-adjacent vertices. First of all, you have to know, hey, what is this vertex adjacent to? What isn't it adjacent to? So that's already a big O of n calculation. I've got to enumerate every single vertex and check for adjacency. Then I've got to check all the non-adjacent ones in pairs. This just became big O of n cubed. No, I don't like this. By the way, this bound is sharp. If you have a graph where the degree of the non-adjacent vertices is even one less, then you could still have a cut vertex or a bridge. These are two K4s that overlap at one vertex. I hope it is clear that this graph has a cut vertex. How many vertices are in here? And if I were to take any two vertices that are not adjacent, notice that all 6 of them are adjacent to this one. So it's got to be one from the left triangle and one from the right triangle. Sum of their degrees is 6. If I'm even one less, I have a cut vertex. I've done it for K4s that overlap at one point, but you can use any K and overlap them at one point. You could use a complete graph of any size, overlap one vertex, and you've got a cut vertex, the 2kn minus 1, 2k minus 1s. You're guaranteed to fail Orr's condition. So I seem to have a minimum degree requirement by pairs of vertices. What a pain in the ass. How can I make this easier to count? How can I guarantee you that I will have this condition be true? Where I only have to look at each vertex rather than pairs of vertices. I don't want to look at pairs of vertices. I just want to look at single vertices. I guarantee you this condition will be true and still only have to look at one vertex at a time. Let me phrase this differently. What's a condition I can put on every single vertex? And I can then conclude the sum will always be bigger than or equal to n for any two disconnected vertices, non-adjacent vertices. I need you to fill in the blank.
Would be if degree of V is bigger than n over 2.
Exactly. If the degree of v is bigger than n over 2 for every vertex, then when I add two of them together, I get something that's bigger than n. Huh. So if I average out the degrees so that every pair combined gives me n, then each vertex needs to have n over 2. Right. Now, if n is odd, then clearly I'm going to use the greater than, right? But if it's even, that'll be a sharp bound. So now I don't have to look at pairs of vertices. This just got faster. Is it trivial? No, because I have to go through every single one, and it is still not enough. It is possible that I could have vertices of degree smaller than and still have a Hamiltonian cycle. This is this is sufficient, but not necessary. I know we talked about necessary and sufficient conditions if and only if this is only a one-way street. So maybe I should work with the proof of Orr's theorem. In Orr's theorem, we kept adding in edges. And somewhere along the line, we said, ooh, I've got a Hamiltonian cycle. And if all of a sudden I had a Hamiltonian cycle, then we had to have some issue with degrees. But what if I was actually able to say, no, we have a Hamiltonian cycle every step of the way? If I do satisfy this Orr's theorem criteria, and I take any two non-adjacent vertices, and I add in that edge, Orr's theorem showed we couldn't go from non-Hamiltonian to Hamiltonian. If I know that Orr's theorem condition works on the degrees, then every step of the way I had Hamiltonian. Huh. I'm repeatedly adding edges. Eventually, what do I get? Complete graph. So somewhere along the line, one of two things happens. Either I end up in a complete graph, or this condition was broken, as we saw in Orr's theorem. So if I have the condition, then I should be able to recursively create a new graph by adding edges and bringing the sum of the degrees up. We're going to create something called the closure of a graph. And we create the closure of a graph by repeatedly joining non-adjacent vertices whose degree sum is at least n. Here's G. I'm going to label the vertices clockwise from the top. How many non-adjacent vertices do I have? All right, how many pairs of non-adjacent vertices do I have? I got a lot, right? A is not adjacent to C, D, or E. B is not adjacent to D or E. C to A or F, and symmetrically around D, E, and F, right? So take two non-adjacent vertices whose degree sum is at least n. Two vertices that are not currently adjacent, whose total degree sum is 6 or more. Wait a minute. Minimum vertex on this graph, minimum degree of the vertex is 2. Maximum degree is, so I need 2 degree 3s to get a degree 6, right? I have F and C, or, and that's it, right? So, step 1, adds those two. But now the maximum degree of this graph has gone up, which means I have vertices of degree 4 that I could combine with some vertices of degree 2, right? What vertices of degree 4 are not adjacent to vertices of degree 2? All right, say that again. Aha. 4 to 2, 4 to 2, 4 to 2, 4 to 2. Perfect. So there are the 4 edges you just named for me, Ben. Great. Resulting graph. A to C, A to E, D to F, D to B. Wait a minute. What's the degree of B? Somebody said it. B? B. Degree of B, 5. The degree of D is 4. The degree of B is 5. Degree of C? E. F. There are only 6 vertices. Those are connected to everything now. There's nothing those are not adjacent to. Which means the only possible vertices that are still not adjacent are A and B. Are they adjacent? No. What's their degree combination? The degree sum. Which is bigger than 6. Degree at least n. Step 4. I'm sorry, step 3. Add AD. Hey, wait a minute. What graph is this? I made it all the way to complete, right? Which is what we said was going to happen when we were doing force theory. Now, some graphs, there are no vertices that have this property. Consider the graph C6. Now, you might say to yourself, this graph is not all that different than the graph I started with in the previous example, right? What's the degree of every vertex here? And if you take any 2 non-adjacent vertices and you add the degrees together, you don't get a number that's at least 6. So the closure of C6 is C6 itself, because there are no additional vertices to add. Bipartite graph K23. What's the closure of that graph? Is 5. From left to right, everything on the left is already adjacent to everything on the right. So I only need to look at non-adjacent vertices. So what can I possibly add? Aha, degree sum on this side is 6. Add those because the total n is 5. So the closure of K23 looks like that. I add one edge and that's it. Because of the way Orr's theorem worked, every step of the way along the process here, I had that degree sum bigger than or equal to n, yes? And the only way in Orr's theorem that it fell apart was if somehow that degree was less than or equal to n minus 1. So as long as that degree sum is holding in the first place, I have this lovely theorem. A graph is Hamiltonian if and only if its closure is Hamiltonian. And that's really what Orr's theorem told me. Orr's theorem said that nowhere along the way can you switch from Hamiltonian to non-Hamiltonian without violating that degree sum property. What graphs do we know are always Hamiltonian? So if my closure is complete, my graph must be Hamiltonian. My problem, and it's not small, it's big. I don't have a if G is Hamiltonian then, with the exception of this one, which requires me to make the closure of the graph a recursive process that does not look at all simple. So what we end up stuck with repeatedly, every time we try and find one characteristic, this graph is going to be Hamiltonian, is one of two brute force algorithms. Start looking for one, or start counting pairwise degree sums, or individual degree sums. Blech. Well, it turns out A guy by the name of Posa actually came up with a direct degree counting behavior. I want to count the vertices whose degree is smaller than half the order. What? Posa's theorem says the number of vertices of degree j for all j between 1 and n over 2 is less than j. How many vertices of degree 1 can I have? If my graph is of order at least 3, the number of vertices of degree 1 must be less than 1 for my graph to be Hamiltonian. You can have no n vertices, which makes sense, right? Because if you have an n vertex, you go across that, you come back, that's not a cycle anymore. But similarly, how many vertices of degree 2 can I have? At most 1. I need the number of vertices of degree j to be less than j, up to half the size of the order. If my graph is of order 100, I now have an upper limit on the number of vertices to be degree n for that graph to be Hamiltonian. Instead of counting pairs of degrees, I have to count individual degrees. Again, this is a proof by contradiction, and we build the closure of the graph to determine it. But I've got 30 seconds left today, so I'm not doing this proof. Questions? I'm making circuits to go across certain graphs. I'm making cycles to go across other graphs. People, I'm doing this to travel around my map. Have you been in Pittsburgh? What's wrong with the roads in Pittsburgh? There's none of them that are one way. Every one of these graphs has been undirected. How does all of this change? When I start thinking about digraphs, which are real life. Later.